Everybody, thank you for joining our session. The title of this session is Universal Timekeeping in Space, Moving Beyond Earth as the Reference. And our speaker today is Stephen Moore, founder and CSO of Vatis Space. If you have any questions, please type them either in Hoover platform or in chat or in Q&A here in Zoom, and we will address them after the presentation. Thank you, and I would like to give the floor to Stephen.
Thank you very much. So good afternoon, everybody, and thank you for taking time out of your schedule to listen to the talk. So as mentioned, my name is Stephen Moore. I am the founder and Chief Science Officer of Vatis Space. So to kind of get everybody in the same mindset, what we're going to be talking about is time. So when we look back at Einstein's quote, it says, time and space are models in which we think and not the conditions which we live. This is very poignant to this conversation because we're going to be introducing another way to model time, a way that's outside of relativity. So humanity is really preparing for its next giant leap. So about over 50 years ago, humanity took their first steps on the moon. And since that time, we've learned a lot about our solar system, but also exoplanets orbiting other star systems. So this really brings into the question, well, have you got the time? What is the time on these planets? So there is a problem. So what is the date? Is there a calendar system? And what is the time on any given planet? It could be any given asteroid or even any given moon. So how do we model time and harmonize calendars simultaneously in space? Now, this is a problem also because there's a universal timekeeping solution that doesn't exist for space exploration. So models for time, the theory of relativity, create a lot of issues, and we'll talk a little bit about that. Currently, radio signals are used to synchronize clocks around Earth, and this is through a relay system of satellites. And this accounts for the delays of gravity and other external influences that carry these signals. This is very computer intense, very expensive. And once we can begin to explore beyond Earth, we start to see practical limitations for this technology. So another problem that we have to address is that Earth is not the center of the universe, and not physically, like Copernicus described to the Europeans many, many years ago, but also not in regards to temporal space. Now, to address these problems, an ask was delivered by Washington in April of this year. So this was a memorandum put out to, as they say, establish time standards that consist of definitions, development, and implementation of a distinct reference time at each celestial body and its surrounding space environment. I'll talk about this throughout the talk, especially calling out how they're asking for a distinct reference time at every celestial body. The key features of this ask included 4 things. Traceability. So traceability to Earth's UTC. This is our time system that we use every day and our computer systems use every day. Second one is accuracy. So we want to support an accuracy that works with navigation systems as well as for scientific exploration. Third is resilience. Resilience means that if there's a loss of contact to Earth, whatever celestial body is setting up time still has the ability to maintain a time system. And lastly, scalability. This is where the space environments beyond the Earth and Moon system can adapt to the same framework and same consistency of the planet. So now we were given this ask, about 5-6 months ago now. And since there has been a lot of exploration and a lot of discussion around this. What I want to kind of emphasize in this talk is that there's really 2 buckets of conversation. The one that is getting all the press, all the publications, and a lot of the attention of commercial as well as governments is in the navigation and communication systems. This will take billions of dollars to implement, and it'll take a lot of computations, and this hence the publications. So the purpose here is to synchronize radio signals to and from Earth. This is to set up PNT, or position, navigation, and timing requirements. There's a lot of work from international space agencies, universities, and other communication entities. And what there's a LunaNet standard, and everybody's looking to align to these standards using various space clocks and calculations to align for a synchronization of the signal and time coordinate. The second bucket, which we'll be talking about today to give context, is in n-body timekeeping. So think of it simply as clocks and calendars. So this is the emphasis of Varda Space. We have a methodology that utilizes various sources or clocks. So we use interstellar as well as intrastellar data sets. So this can include space clocks on the moon, but it can also include Doppler-based methods so we can understand the orbital velocity of planets, and this can be brought into our timekeeping system. The limitation of the n-body timekeeping or clocks and calendars is limited by the technology of the measurements, not by the methodology. One of the major proposals out there right now as we start to look at time on the moon is presented from the National Institute of Standards and Technology. So recently there's a paper out by Ashby, and the proposal is that we've set up this satellite network around Earth, and this works fantastic for setting up navigation and communication systems. The idea is really here to set up an extended satellite infrastructure out to and beyond the moon, so that even the relay satellite network is exposed to the Lagrange points. So the idea really here is to extend Earth's daytime and time system out to the moon and synchronize radio signals originating from Earth. But there are problems here. So it requires continual adjustments for the relativistic effects on time. And it also has delays from Earth because you're using a radio signal. So to simplify it here, just looking at direct path, you have a ping from Earth at 0 time. It takes a while for that radio signal to get to the moon, about 1.3 seconds. So if you use a ping and a radio signal to create a time coordinate on the moon, you're already delayed as soon as you sent it. And in the delay in this case, when you get 0 time on the moon, that's 1.3 seconds have already passed on Earth. What happens is this creates an asynchronous environment. So the real world environment on the moon is not synced to the time on the moon. So this can affect the day and night cycle as well as the orbital periods don't get a proper alignment to what you're calling time. And this is also exceptionally expensive to implement. When we look beyond the moon, we get the signal pin out from the radio signal. And when we start extending into, say, Titan, which is a moon of Pluto, or Jupiter, sorry, all the way out to Pluto, and then let's extend even further and go to exoplanets of other star systems. You can see that by the time you get to Pluto, you're looking at over almost a 9-hour delay for a T0. And when you get out to the celestial planets of other star systems, could be years before they receive their 0 time index from the moon. And a part of all this, you need to have an intercelestial satellite infrastructure and computational needs that are not that scalable once you start talking about other star systems. So the key takeaway here is regarding the NIST proposal for clocks and calendars is it's not resilient. This depends upon a radio signal originating from Earth. If Earth no longer existed, time would not exist in this definition on those other planets. It's also not scalable, as I talked about. It's impossible to set up the satellite infrastructure all the way to another star system. And it does not synchronize with the real world celestial motion. Once you get up to Pluto, for example, it's not tied to the daylight set of the planet's orbital rotation or axial rotation, sorry. So when we look kind of at the proposal for NavComs, which are very effective, we're experts in that. We've been doing it around the Earth for quite some time, and extending out the grid to the moon makes a lot of sense for navigation and communications. But is the LunaNet approach applicable for interstellar clocks and calendars? Consistent methodology for all applications. So when we look at that, we look at traceability. Yes, it meets the traceability for the moon. And yes, it would have a UTC alignment, although it would be quite delayed. The accuracy, yes, is predicted to be within the call out of White House and what they're wanting. But the 2 key points is that it's not resilient timekeeping. It is dependent upon radio signals from Earth. So if Earth all of a sudden had a disaster, time essence shuts down on the moon. It's also not scalable. It's difficult within the inner solar system, but it might be possible, but it's conceptually impossible for the outer solar system and even interstellar bodies. So once we look at the issues for multi-celestial clocks and calendars using a NavCon's proposal with radio wave signals, it also requires an Earth-centric proposal that ignores the local cycles and periods like day and nighttime on different planets. There's also no possibility to have a synchronization to the present. It only synchronizes with a past signal when it originated from Earth. This is through relativistic calculations. So let's look at both of the situations together. We agree nav communications work fantastic, and this is what we need, especially when we get out to the moon. How does this work with multi-celestial clocks and calendars? Well, think of NavCom as set up using radio wave communications. There's space-time delays because the radio waves travel at the speed of light. But there also needs to be continuous adjustments, even for like gravitational fields or even an earthquake on Earth. The proposal here being put out in the literature is to use a relativistic framework, which is a well familiar framework proven in various scenarios. In this setting, you have one event in space, and it's observed from 2 points, either the moon and the Earth, for example, and that will give 2 different time coordinates. So there's a lot of different calculations that need to come into place. On the other hand, when we look at clocks and calendars, what we're looking at is time flowing through a point, not flowing through space. Now, this is coming out from recent publications, and it's referred to as a relationalistic framework. The publications are shown there. In this setting, there are no inertial frames. It doesn't use the same criteria, the coordinate system that you use in relativity, so time is modeled in a much different approach. By doing this, you set up the ability to set up an n-body timekeeping system. So just like we have time on the Earth, you can have time on the moon, you can have time on Mars, or any other planet with an axial rotation or a circular or elliptical orbit. This can include even asteroids. The important thing here is the technology that Vardis is implementing allows for the timekeeping on the planet to integrate seamlessly into a universal calendar system so that we can create an n-body calendar that eventually, once the data matures, would synchronize not only cyclic time, but also provide spatial positioning of planets in the simultaneous. So as it is on Earth, we would know where it is in another planetary system at the same moment. This isn't possible by relativistic framework. When we look at the first example, Vardis Space is introducing Moon 18 instead of Earth's rotation or Earth's axial rotation split into 24 hours. We're looking at the moon's orbit around Earth, sort of the lunation cycle. So this is a framework that is open for consideration as a coordinated lunar time, and it's dependent upon international collaboration. But instead of doing 24 hours in a day, what we're doing is 18 divisions of lunation. It's kind of like an hour-like, and then that is further broken down into 20 first-order divisions and 20 second-order divisions, creating a total of 7,200 mets, if you will, or seconds. Now, this is not arbitrary. It actually aligns to a lot of ancient calendars and publications around the divisional structure of the Mesoamerican timekeeping system. This provides an independent time on Earth, independent of any time frames or time zones that we would have on the planet. So if you're in China, if you're in Canada, the North Pole, the South Pole, your Moon 18 time would be exactly the same, or even on the moon. And that brings me into this slide. So where do we stand right now? So we are looking at Vardis Space of implementing 4 different steps. We've already completed first step. We're looking to expand upon it, but the second step is moving beyond Earth. So this is to look for collaborations and R&D and implementation. So in this setting, what we're doing is instead of using a radio signal to align time, we're using a signal at a point. So not looking out, but what's coming into that point. And in this application, we can synchronize the clocks on both the Earth and the moon without any time delay in between. So we're using the lunation signal of a new moon. And when the new moon hits, time on Earth hits 0 and time on the moon hits 0. And each one is in a different inertial frame of reference, but each one is experiencing the same event. And this is how we can synchronize the calendars or the clocks and calendars. Once we have implemented step 2, when we extend out into the surrounding space or even out to emissions into the moon, and then we set up a ground system of a lunar calendar or a lunar clock. And this can be working with existing systems and projects that are already in works to put an atomic clock on the moon. The step 4 would be to create a resilient LTC. Now, this resiliency is different than the proposals currently, because this can function with loss of contact to Earth. So once the proposal here is that once you set up an independent clock for the moon, you can have that clock run its own surrounding space. And so this becomes its own independent frame of reference, just as we use 24 hours in a day, et cetera, to surround the space of the surrounding space of Earth. You would do the exact same thing for Moon 18 and the surrounding space of Moon. It is also capable, based on the design and calendar systems, to have an observational-based time synchronization with Earth or other distant celestial bodies, for example. This is very important. If there's a loss in contact, you can maintain what day, even probably what hour it is back on Earth. Beyond a clock, we introduce the calendar system. Now, in this example, it's just a two-body part of a multi-universal celestial calendar system. So you can layer on every single orbital body or every time period in the universe, really, theoretically, and build upon each other. So what we're doing is linking a primary rotation or period of 13 lunations, called the lunar terrarian year, with 384 days in a regular lunarian calendar year. So this is deviating from the Gregorian calendar, which is used in a lot of places on Earth, but it is aligning to a calendar system. Again, this is not arbitrary. It's a hypothesized system in the ancient Egypt before the Greek influence. And it was originally coined from ancient China in the study of Neolithic structures, and is similar to findings in Mesoamerica. It's also consistent with the structure of the Vedic and Hindu timekeeping system and ancient Chinese mathematics. When we extend this out and look at how does this scale, we look at N-body implementation. So the navcoms can work in conjunction with local clocks and calendars that organize the surrounding space of each planet or moon. And we bring in components from mathematics, which is called discrete event simulations. So we can create object-specific formulas for every single object. So for example, if we want to stay consistent to a planetary rotation of 24, we would say Earth 24, Jupiter 24, Pluto 24. This is already used for Mars 24 and implemented. And for the other scenario, we would divide a moon's orbit into 18. So you'd have Moon 18, Titan 18, for example. And this division of time immediately represents whether or not you're a planet or whether or not you're a moon. When we get out further and we don't know rotational speeds, or even if there's satellites or moons for a planet, like for example, if we look at SETI F, we look at the orbital period, and we can use Doppler technology for time and give an approximation of the orbital velocity or years of the planet or the orbiting mass. So we can create calendar systems that are inclusive to this, that extend as our measurements increase. And the takeaways here is that we have the ability to create clocks and calendars that is separate from navcom delays, and it creates an environment unique to itself, so a distinct reference time at every celestial body. And as shown, it is scalable. Now, this isn't also a standalone system. This is an interconnected framework that can be extended well beyond. We can look at taking examples as we get more information, as we get more of a footprint on different celestial bodies, like the moon, for example, putting an atomic clock there. We can switch from mean times and mean orbital time into exact coordinated system with atomic counts. It's the same precision that we provide seconds and definitions of SI units today. We also give the framework here an N-body SI unit system. So every single celestial body will have its own SI units for time. And so the expansion of the of the International Standards Bureaus will say a second on Earth is defined as this by cesium-133, or a second on or a METS on the moon is defined by this as defined by our cesium-133 counts. So it creates a framework for expandability, and as more information has come, more precision and details can be added to it. When we look at the Varda space proposal and the multi-celestial clocks and calendars, and then compare that with the ask from the White House, we hit all points. So we're advancing theories with relationalism, temporal space. These are all publications that have been peer-reviewed, and we're redefining concepts. We're adding traceability to the UTC. It's theoretical that it would provide this link. The accuracy is also in theory, precision to a few 10,000 nanoseconds. These two top points have a box around the check marks because, of course, further research and development and testing is needed, but this is a theoretical prediction. When we look at the resilience, there's self-sufficiency. They will exist. Time will exist with loss of contact with Earth. You can actually, even through the calendar system and alignment of synchronization, keep track of time on Earth if you were to lose track. It's also scalable. You can use it to include any celestial body cyclic motion that can be measured. This can be a star orbiting the center of the galaxy, for example, a planet orbiting a sun, a moon orbiting a moon, for example. Now, going beyond, it does develop new definitions, and like I mentioned, and it's capable of expanding beyond standards. So, well, have we got the time? Well, yes, we do. So we already have an existing iOS product for the consumer market that includes Mars 24. And this is calculations already given from NASA that are publicly available. And we also have a Moon 18 time as discussed in the system. This is ready for more accurate data repositories to link to, and also it increases the ability to do scientific study and development, so we can take the next steps in deployment in the surrounding of Earth, and then ultimately into the moon itself. So in summary, there is an effective way to model time that's an alternative to the relativity framework. This framework is synchronous for clocks and calendars. There's a distinct reference time at each celestial body using a relationalistic standpoint or framework. And that, if you will, distinct reference time becomes applicable for surrounding space environment where you would build in relativity and the necessary calculations you'd need for the NavCom communications at that celestial body. This is a part of an interconnected universal calendar system that can be expanded to n bodies in the universe. The technology we're using is really actually embracing a lot of the ancient timekeeping principles and combines that with modern technology, physics, mathematics, as well as increasing definitions and development. And we're looking for planning and international consideration. Right now, we have existing customer product called Vardas 12. This is where we have Moon 18 and Mars 24 clocks already available for your phone and watch. This creates a celestial body time for these two bodies that is independent of Earth's time zones. The Earth-Moon system is capable of establishing the sunrise and sunset tracking on the lunar surface using using Moon 18, and it's ready to expand upon. So with that, I'll conclude. But so we're at Varda Space. We tell time and space. So eventually, our astronauts on different planets and different moons will be able to answer the question, have you got the time? So thank you for your time.
Thank you, Stephen. If anybody has any questions, please type them now because we only have 5 more minutes. If nobody has... Oh, there is a question. It's just a comment from Wendy. She says, thank you for the informative presentation.
Thank you for your attention. That was great.
If nobody has questions, we are going to end the session. Thank you, everybody, for joining. We have some more sessions today, so please check our website and you can join other sessions as well. Thank you, Stephen. Bye-bye.
Thank you. Bye.